computer systems, and he has worked for more than 4 years in the field of robotics and electric vehicles. He has completed his BTech in automobile engineering, and he has worked on miniature robotics, robotic manipulators, and compliant robotics along with computer vision. The second expert who is going to deliver today for this session is Mr. Kaif Bojani, who is a robotics electronics R&D engineer. He is an electronics and telecommunication engineer with experience of working with R&D in automation and IoT. His primary focus is on implementation of various automation and robotic systems. So I would now like to request the first expert, Mr. Kushal Das Badan, to please start with the session. We are able to see the slides, but we are not able to hear you. Hello? Okay, so the expert is just checking his audio settings. I request all the participants to kindly wait.
Hello.
Yes, now you're audible. Yes, now you're audible. Please share your screen so that we can start.
Yeah. One second. Okay. Is the screen visible?
It's about to start. Yes, okay, sir. We are good. We are good. Please go ahead.
Okay. So basically, SVR Robotic works in different robotic systems, which might have different application. For example, inspection, maintenance in industrial environment, or in defense and security related applications, or in educational applications, or even in some testing related application. So first is basically curl. Curl is compliant universal robotic latch. This robot is developed for pipe inspection purposes. So if you see, the architecture of the robot has a crawling segment, rolling segment, and camera and gripper segment. And this robot is tethered. So tethered is specifically so that if there is any failure in the robot, we can use that same tether to pull the robot out. And it can enter pipe diameter of 75 mm. And so basically on this gripper, on this robot, we can mount a gripper or a camera at the end to perform operations like inspection and maintenance. So here is a video of rolling segment operation. So the rolling segment basically utilizes this mechanism which rotates that segment from inner side. So this is another video. So here you can see, and this is basically the external cam which actually interacts with the environment. And if you compare the size of this rolling segment with a 5 rupee coin, this is basically the size of the robot or the segment. So this is basic mechanism of working of the rolling segment. So what it does is it has a external cam visible here, and if the rolling segment has to roll, what it does is it is actuated from inside. It basically rotates from inside, and when this surface basically comes in contact with the ground, instead of rotating, so the cam stops rotating, and instead the relative motion is produced in the body of the rolling segment itself. So this is the internal exploded view of the rolling segment. So it uses an external cam which has internal gears and a pinion which is driven by an actuator, and then whole system is housed inside a aluminum body. So this is the assembled view. So here you can see where the gear basically meshes with the internal pinion basically meshes with the internal gear, and how this motor is basically housed in the casing. This is basic mechanics of the rolling segment. So basically the T applied is basically the torque which we will need to rotate this robot, and T friction, that will be a sum of T friction and T inertia. Friction will be basically this friction produced between the robot body and the ground surface, and T applied will be the torque applied by this external cam. And we can calculate that using inertia, that will be I into alpha acceleration and mu into W. Then this is basically these are the loads which are acting on different parts of the robot. So here you can see external cam, and then we have motor mounting plate. Then moving on to crawling segment. So crawling segment is gets attached in front or behind the rolling segment. So purpose of this segment is to actually move forward. So here you can see working of the crawling segment. So the crawling segment has internal mechanism which and operates on two legs. Each of the leg is controlled by individual actuator or individual motor, which is basically DC series servo motor. This is internal view of the crawling segment. So here you can see various linkages, and this red part is basically the legs of the robot. And here you can see there are two motors which controls each leg individually. So this is so that we can have maximum control over the robot, and we can control speed of each leg individually to achieve different kind of motion. This is the actual mechanism which is utilized in the crawling segment. This is called clan mechanism. And here we have input side where we connect the motor, which is basically rotary motion. And at the output side, it produces triangular kind of motion. And this horizontal line is the stroke of actual movement. Then moving on to gripper. So gripper is the rack and pinion type of gripper, and it also uses similar kind of actuator. So basically, what happens is there is this pinion which moves these racks, and these racks are basically connected to jaws of the gripper. So this is photo view of the gripper. Then earlier was rolling and crawling segment. Then we have also developed wheeled mobile segment for the robot, where pipes are not that rough. We can use wheeled segment, and wheeled unit is a complete system with camera and a gripper. So here you can see here we have gripper motor, and the gripper mechanism here is different. So this is a much larger view of the same robot. Again, here we have individual motors which operate individual wheel. This is again for maximum control of the robot to achieve different kind of motions. So here is basically how the gripper operates it. The motor is attached to a semi gear, and this semi gear again meshes with another gear, and combined they produce a parallel gripping motion in the gripper. So purpose of this gripper is, for example, there can be some kind of debris or some kind of part which might be blocking pipes, any kind of pipes, for example, in power plant or in boiler kind of application. There can be some piece of metal. We can remove that piece of metal or some whatever the debris using this gripper. Then camera module. So it is simple camera which basically transmits data in the form of audio and video. And this is the actuator. So this actuator is basically a DC series servo with a small gearbox with plastic gears. Then moving on to flexible link with flexible shaft driven manipulator. So this is our research project where this robot utilizes flexible links which are driven by a flexible shaft. Main advantage of this kind of mechanism or this kind of design is weight of the links is very low, and as we are placing all the actuators for each joint in the base, again we are reducing weight, so total inertia of the actual manipulator will be much lower than what we will see in any other kind of manipulator or industrial kind of manipulator. So here is a earlier prototype. So here you can see there is basically deflection in the links due to torsional and bending moment. So what we can do for here is basically we can increase rigidity of the links, as well as we can use sensors to actually check how much flexing is there in the links, so that we can estimate end effector pose. So here you can see there is again bending. So this robot has one linear joint which moves the whole system up and down, and then there are multiple rotary joints. All the rotary joints are driven by flexible shaft, and then it uses CFRP links. CFRP links. So these kind of robots are very much, or this kind of design is very much useful when we are required to reach a very long, or we are required to cover a very long distance, but there are weight constraints. For example, in space systems, or there is another application in nuclear where we are required to monitor nuclear fuel rods over a size of football field. So at one side we can mount this kind of very large manipulator, and we can cover that whole distance using this single kind of manipulator. Then moving on to sensorized miniature gripper. So this is basically a miniature gripper with multiple sensors to check performance, as well as determine what kind of forces are being applied, and what kind of force the gripper is applying, and what kind of object is being picked up by the gripper. So here is a basic illustration where this gripper is holding this coupling, and here we have a load cell. So as you can see, here we have IR sensor modules, then a load cell, and then strain gauges and a flexiforce sensor. So all this combined can generate a data which enables us to actually determine what kind of object is being picked up by the gripper, and what kind of forces are being applied, so that we can control torque of the motor, or the force applied by the motor, and so it does not squeeze that particular object very much. So this is another view. So here we have this load cell, and then IR modules, then the motor, and these are the linkages, and here we have the gears which are actually operating this whole system. So here is flexiforce sensor, then the strain gauges, then load cells, and then IR modules. Again, another view of strain gauges, flexiforce, load cell, and IR module. So purpose of IR module is basically it checks if there is any part and the distance between the jaws and the part. Then load cell basically is able to check what kind of forces are being applied on that particular object. Then the strain gauges check the deformation in the links, so that we can limit the force, and flexiforce basically check what kind of deformation is being happening at this base part. This is instrumentation of that gripper. So this is as this is research purpose. The instrumentation is much bigger and much complex. But if it has to be deployed in production, the whole system has to be on a single module. So basically, this is the demo of picking up different objects, and on the GUI we can see what kind of forces are being applied, as well as what is the actual strain on the links. Then moving on to next development, which is monocam vision guidance for industrial robotic arm. So here you can see the robotic arm is basically a Mitsubishi make, and the gripper is SVR Grabo, and we developed a system with a simple webcam, which utilizes which basically generates differentiates these different objects and generates coordinate, and then guides the robot to actually pick them. So here is basic working of the robot. So here you can see this is the actual display, and here is the detected object or the object of interest, and in the visualization window. So here you can see this is the camera, yellow part. Then red is basically the manipulator. Then this green part is basically Grabo 1.5. This is 1.5 kg payload gripper, and this is our object of interest. So what happens is this camera will see this object, then it will recognize that object, then generate the coordinates. Then so basically all this is being processed on the computer, and the computer will actually send the data, the coordinates to the robot controller over a Modbus. And this is the actual deployment of the robot. So first it will sort all the green blocks, and then the blue ones, and then the red ones. So actually the camera is not seen in the footage, but it is basically here somewhere on the top. What happens is, so basically, so what happens is once this robot drops here, that object, and it is out of sight of the camera will capture an image, then process that image, then it will generate the coordinates of that object, and then send that coordinates to the robot, and then the coordinates as well as color of that object, so that robot will specifically put in that particular bucket. So each time the object is dropped, a new photo is captured, so that even if we drop something here again, it will be sorted. And for the communication, it utilizes Modbus communication. And instead of using any industrial system or the industrial vision system, what the system uses is it uses a simple webcam, and all data is being processed in using OpenCV. So at this point, this robot has come here and stopped. So if we place another any of the object here, it will again go and pick that object. Moving to next, so this is basically robotic farm worker, which was developed for SEDAC Kolkata. So this is the actual concept that was presented to them. So this has solar panels and then multiple robots at the bottom. And this was the actual design which was developed. So it has dimension 1650 by 1650 and a ground clearance of 1200 mm. And basically it is square in shape. So this distance between the wheels is 1400 by 1400 mm. So this is the actual body of the RFW. And these are actual photos. So it has to be, robotic farm, the purpose of the robotic farm worker is, as there is much labor problem, as well as there are many other problems like child labor. SEDAC Kolkata is basically developing this robot, which will be used to carry out operations in rice farm. So it has to be a mobile robot, and it has to be work in rice paddy. So the design is robust and reliable. It can be used with a path planner using a simple GUI. It has almost zero maintenance, and it can run up to 5 to 7 hours depending on the load. But generally, it can run for a minimum of 5 hours. And it is very much adaptable like a tractor. So we can deploy multiple systems on the robot. So these are basic components. So body, the drive system, and the steering system. The bodies or the main frame of the robot is composed of aluminum and steel material, stainless steel mainly. So yellow is basically aluminum, and green is basically stainless steel. So here again some multiple views. So these are basically brackets which can be utilized. So these brackets are inside and outside of the body, and these can be utilized to attach different attachments below or inside the robot. Then some FA analysis. And then it has roof doors and aluminum body panels. So this is steering mechanism. So here we have steering gearbox above which there is steering motor, and then we have multiple bearings which these bearings are basically used so that there is no direct load transfer to the steering gearbox apart from the torsional load of the wheel. So if there is any lateral longitudinal load, that load will be transferred from this bearing into the frame. So here we have FA analysis of the some plates in the steering system. So this is a steering motor and the gearbox. So we utilized step servo motor and a planetary gearbox. So this is assembly view of the steering motor and gearbox. And then the mechanism, steering mechanism, is basically a basically holonomic drive. So we can have different modes. For example, this is turning radius mode. Then angular four wheel steering mode. Then the crab turn. So basically, vehicle will go in this particular direction. And then zero turn radius mode. This is a drive system view. So here we have this drive motor. Then there is a chain drive, and then here we have wheel hub, which drives this wheel. So here again we have some other views. So this is the wheel hub, and it utilizes basically it is purchased from a OEM. So that and it utilizes two roller spherical bearings. This wheel hub is specifically chosen so that we are able to so as to avoid any load on the drive shaft, and those all loads will be transferred to the actual frame, any lateral or longitudinal load on the vehicle. Then we have some FEA views of the motor or that drive mounting plate. And these are the pipes which actually hold the wheels. Then drive system. So drive basically uses a BLDC motor with a planetary gearbox. And this is the wheel hub sectional view. So here we have two. So here we have two taper roller bearings. These bearings basically isolate any longitudinal or lateral load. So if there is any load on this wheel mounting, it will be transferred to this stationary part instead of this drive shaft, because those loads are very high and it can damage the shaft. So we are basically utilizing this to transfer the load. So here we have FA analysis of this wheel hub. Then moving on to wheel. So wheel is basically combination of stainless steel and aluminum. So the center of the wheel is and the spokes are of aluminum, but the outer part, which will be actually in contact with the ground, it is made up of stainless steel, so as to avoid any wear or any high bending stresses will be avoided. And it is direct in direct contact, it stainless steel avoids much larger wear instead of using aluminum. So here we have some FEA views. Then whole system FEA. Then the battery it uses is basically 48 volt 80 ampere hour lithium ion battery, and it has a peak current of 150 amps and continuous of 100 amps. So in the battery itself, there are multiple protection systems like overcharge protection or over discharge protection, then short circuit and overcurrent protection, temperature protection. And this is the basic architecture of the computers and control. So here we have the onboard computer, which is basically a Raspberry Pi, and then this Raspberry Pi handles whole GUI, and there is a access point connected to the Raspberry Pi using a LAN cable or Ethernet cable, and we can access that GUI using VNC or SSH from a Wi-Fi network. Then the Raspberry Pi actually controls all other systems, like whole actuation is controlled by a microcontroller, which again utilizes multiple microcontrollers to control each drive motor. And then drives of the step row steering motors and the BLDC drive motors. And then there is a relay system which actually controls lights, contactor, and alarms, safety alarms. So this is the Electro Box, because it has electrical as well as electronic systems housed inside it. So these are the bus bars. Then we have Raspberry Pi, DC-DC converters, then contactors, cooling fans, different the relay system, then the step servo drivers and BLDC drivers, and then there is this rail which carries all the wires. So these are different components. And this is the GUI of the system, which is utilized to control the robot. So here we can set up, we can put the mass and silt factor, considering the ground, what kind of ground it is, rigid ground or if there is any mud. Then we can calibrate the robot here. Then we have command module, so we can select different modes like radius turn or zero radius turn or crab turn. And then we have different subtypes where we can put the commands. And then from here we can see different commands are added. We can move this sequence of the command, we can check, and then we can run those commands on the robot. And from here we can monitor the operation, like we can turn on and off light. Then we have emergency stop, which is, so basically we can stop the vehicle from wirelessly from a distance using this emergency stop. So here we have some photos and videos of field tire. So this robot is, so this video shows operating on rigid ground. Then on the grass or lawn. Then the steering system. And here we can see the steering system in heavy mode. So as you can see, it can, so the wheels are able to move 360 degrees, but those are limited to 180 degrees, so that we avoid tangling of the cables. And even though those are limited to 180 degrees, the vehicle can go in 360 degree itself. This is achieved by changing drive direction of the wheels. So instead of moving, so suppose one wants to go at 270 degree, we can move the wheels to 90 degrees and then set the direction of the drive wheel to reverse. Then moving on to Martin, which is basically mobile autonomous robotic target with intelligent navigation. So this was basically a system which was conceptualized by us for simulator development division of Indian Army. So this is the robot which can be utilized for practice of real combat scenarios. So this is the autonomous robotic platform with pre-programmed manual or semi-autonomous modes, and it can be controlled from a ground station which can be away at 1 kilometers. And it has a 3D mannequin, a rubber mannequin, and a GUI app. So these are the dimension of the robot. It can run up to 12 km per hour and can climb at 16 degrees of gradient. It can run up to 3 to 6 hours, and there is onboard a single GPU computer to control the robot. So this is basic control system. So here we have single board computer which communicates with localization and sensor modules. Then the drive system, communication module, and other sensors like heat detection sensor. And this is the software architecture. So here we have Linux on which we run the ROS and the SLAM. The ROS basically utilizes these different sensors and also communicates with communication modules. And here we have ground station, which again has Linux. and there are two modes of control, like from the application and from the joystick. So this is the onboard computer. Then the armor. So armor is basically steel plates with 4.2 mm thickness, and there is anti-spall coating on the steel plates. So spall is basically the shreds which come out of armor after hitting a bullet. So it can be very damaging to the firer in close or point blank position. Then here we have a detection sensor. So this is utilized to detect any bullet hit, so that we can put that robot down during the practice. Then this is a rubber 3D mannequin, and it can take up to 4,000 to 5,000 bullets. So this is the perception system. It utilizes 3D lidar, IMU, and GPS, and the data from these sensors is fed to a SLAM algorithm, which will generate 2D and 3D map data, then the pose data of the robot, and 3D 2D occupancy. And then there are ultrasound sensors to detect any close obstacle or close proximity obstacles to avoid emergency collision. So this is your perception system. This is basically description of the 3D data. Then the IMU and the GPS. Then the ground station. So here is the basically communication and messaging system which communicates with the ground station. Then this is so ground station is basically tub book and a rugged military grade joystick, which connects with the computer. Then the communication. So it uses two communication. The first is basically to transmit text kind of data, or low data size information, like control signals. And 4G communication system is used for transmitting audio and visual, audio and video data. Then the BLDC geared motors and wheels. So it is a solid tires, as it has to take bullets. Then fire localization model is when practicing, the security forces or the person who are practicing also need to be showed on the application. So for that it utilizes IMU plus GPS sensor to actually locate those firers. And this is a complete system configuration. Then another is basically Spider Eye robot. So it is tracked surveillance robot. It has capability to climb stairs and has long standby time. And two-wheel surveillance or reconnaissance robot. So the main purpose of the robot is to act as a reconnaissance unit in during the combat. So this is a robot which is being developed for fusion chamber maintenance. So here it is 10 kg payload and 5 degree of freedom manipulator. It has this, so it is mainly made up of aluminum and it utilizes low backlash speed reducers with BLDC combined with BLDC servo motors. Configuration. So we have first joint, then the second, then the third, then here twist joint fourth, and another fifth joint. So actuators are BLDC motors with BLDC motor with absolute multi-die encoders and speed reduction of strain wave gear type. and it has aluminum links with ROS integration and a different sensor like camera mounted on just before the gripper and force and torque sensing. So these are the grippers utilized for the robot. It has 2-in-1 module, that is parallel and curvilinear. Sorry, parallel and curvilinear, and overhead camera which is able to look exactly what kind of things are being picked by the gripper. And this is the dual configuration system. Here we have a smaller version of that grippers, which is Grabo 1.2. So here is actual operation of the gripper. And here it is picking up 1.6 kg block. Then this is the ECG that is developed by us in collaboration with BRC. So this is 12 and it can communicate through Bluetooth so as to generate reports on the smartphone as well. So next section will be taken up by Kaif. One second, he will connect this. If you have any question, you can ask in the chat or you can unmute the mic and ask.
So till the time the next presentation is started, if there are any questions regarding this, I request participants to type in chat or you can unmute and ask orally also.
Hello.
Hello? Yes, sir, you're audible.
I would like to ask a question.
Okay, please go ahead.
Okay, so as you said in gripper, which type of means electronics is used? I can see the servo motor over there in the center, as you can see.
Okay, just a second.
Yeah, sure.
I think he's not in the meeting. Mr. Kaif, will you please share your screen? Yeah, he's back. Mr. Badan is back. I request you to please repeat your question, sir.
Okay. So as you can see in the gripper, which type of power supply is used in the?
In the grippers, right?
Yes.
Yeah. So basically, the 1.2 kg gripper has a DC motor, and the power supply is 5 volt and 2 ampere.
Okay.
And in the larger grippers like 5 kg and 10 kg gripper, the power supply can be DC as well as AC, depending upon the application. So there are also option of 3-phase AC supply for 5 kg and 10 kg.
Okay. I would also
Is there any other?
I would also ask you in this RFW in robotics farm worker, which types of motors are used to drive that 4 wheel?
So for the driving purpose, it uses PLDC motor, and we utilized Hall sensor of those same motors to exactly control the speed or the RPM. And for the steering purpose, we utilize step servo motors.
Servo motors. Okay.
And there to both the motors there is a speed reducer, planetary gearbox.
Planetary. Thank you so much.
Okay, thank you, Kushalash. Shall we request Mr. Kev to please share his result?
Okay, yeah. Thank you all for your time. If you have any other question, you can also mail later.
Sure. Thank you for the nice presentation.
Hello. Can everyone hear me?
Sir.
Yeah. So can you see the screen?
Yes, sir. Yes, sir. We can see the screen.
So hello everyone. This is Kev Bhojani, robotics electronics engineer at SVR Infotech, and with me I have Karan Jagtap. He's also an electronics robotics engineer at SVR Infotech. So today together we are going to explain you the entire hardware and the software involved in designing a robotic arm. So basically, the name which we have kept for this robotic arm is a multi-gripper robot. The name multi-gripper robot is because we can attach different grippers to this robot as per our requirements, and then do some applications which are required. So now the introduction will be given by Karan.
Hello everyone. Robot has an open source architecture indicator, and it can be flexible with different applications. It is basically payload of 0.6 kg. Then picking up the automation to the industries from placing the different application from different areas. In basically the application of robotic painting, robotic welding, robotic removal. So it is a basically pick and place robots can be customized to fit specific production, moving large, small, heavy, or hard to handle products can be easy to dock to automation in the factory line.
So the block diagram of the robotic arm is as given in the screen. So as you can see here, we have used a power supply which is basically an SMPS of 12 volts and 30 amps. So this power supply was selected by calculating the efficiencies of the buck converters and the current requirements and the voltage requirements for individual motors. By doing these calculations, we chose this power supply of 12 volts 30 amps. And this, as you can see, it is of 12 volts. So we had to use buck converters to actually power up the motors. Hence, we had to use two kinds of buck converters, that is 12 volts to 7 volts converter and 12 volts to 6 volts converter. So now you can also see there is a current sensor interfaced in series with the motors. So basically base M1 motor link 1 motor link 2 motor and M4 and M5 motors. So these are the motors which drive each link and each part separately. Now, as you can see that the current sensor is interfaced because for the protection of these motors, and hence the power supply is given to the motors via the current sensor. And the current sensor's analog output is also given to the Arduino Uno. It is also given to the Arduino Uno. So hence the current sensor gives the analog values to the Arduino Uno, and hence if any situation occurs in which the motor is heating up or the motor is about to get damaged, hence the Arduino can cut off the power supply and the motor can be saved from getting damaged. And the signal pins are also connected to the Arduino. Signal pins of these motors are connected to individual digital I/O pins of Arduino to give PWM signals to the motors. Hence, the motors can achieve particular angles.
Controller we in this multi-gripper is Arduino Uno. You can see on the screen the pin diagram of Arduino Uno. It has 14 digital pins, 6 analog pins, uh, power jack, and crystal basically this inbuilt crystal in Arduino Uno controller, 16 megahertz crystal. The Arduino Uno is an open source electronics platform based on easy to use hardware and software. It programming it has a very familiar to the us, which is basically C, C++. With the Arduino Uno, you can design and build devices that can interact with surrounding. The Arduino Uno are basically a tool for controlling devices. So it is an easy to understand for educational as well as industrial purpose. So that's why the controller is Arduino Uno in multiple robot. Then this is the type of Arduino Uno. In Arduino Uno, there are different types. Arduino Uno, Arduino Mega, and Arduino Nano, uh, Arduino Micro, Arduino UN, Arduino Micro. This is the basically types of Arduino Uno, and depending upon types, the features are different for different types. Its memory and timer will be changed. Then the controller in Arduino Uno, which is the microcontroller that is IC used in Arduino Uno, that is Atmega 328P, this is AVR familiar, created by Atmel. Atmega on the Arduino comes pre-programmed with a bootloader that allows you to upload new code without the use of an external hardware programmer. It communicates using original STK500 protocol. So and digital pins in use this IC is 11, 12, and 13 pins. At Mega, there is 17, 18, and 19. So, although we have many controllers at Mega Theatre, it is most popular controller. That's why we used with the program memory of 32 bytes at Mega and the SRAM memory of 2 KB. The supply voltage is it operates on 3.3 volt or 5.5 volt, 5.5 volt. 32 kb and 28 control it is basically. So then correct.
Yeah. So basically, the power supply which I mentioned, we are using a switch mode power supply. The reason for using this SMPS is that it is more stable and has less fluctuations in the power. Hence, and it can also be driven through an AC source or a DC source, and it can switch your voltage to the desired level. And then it basically you as its name suggests, it uses switching for regulating the voltage, and the switching is done using the MOSFETs, and therefore the output has a high efficiency. Hence, it is used for the AC to DC conversion or DC to DC conversion also. Hence, the SMPS is used of 12 volts, 30 amps. Now, the SMPS works on a very basic principle, that is the block diagram you can see over here is that the transformer first steps down the voltage from AC to 30 volts to given 12 volts or 24 volts. Then a rectifier is used to convert the AC voltage to DC voltage, and different kinds of rectifiers can be used, and depending upon your application. And after the rectifier, there are some pulses and there are some residual noise present in the voltage. Hence, it is not very smooth and it is not very constant. To remove that ripple from the uh, voltage, DC voltage, a smoothing circuitry is used. So this smoothing circuitry basically consists of resistors and capacitors to smooth out the voltage, and a regulator in the end is used to give the desired output constant voltage. Regulators can be a simple IC such as 7805, 7812, or the regulators can also be created using the MOSFETs by PWM switching, and the output of the regulator is given to the load. So now, after we get 12 volts at the output of the SMPS, we now need to convert it to 7 volts and 6 volts respectively. So why do we need to convert it to 7 volts or 6 volts? Because the servo motors we are using run on 7 volts and 6 volts particularly. Hence, we step down the SMPS output voltage using the buck converters. Now, these buck converters are basically DC to DC converters which operate on the PWM principle. As you know, the PWM the PWM principle is like, if there is a duty cycle of 20 milliseconds, in which if you keep the supply on for 20 milliseconds, then you will get 5 volts. And in case if you keep the power supply on for 10 microseconds and keep the power supply off for 10 microseconds, so the duty cycle is reduced to 50%, and hence if the voltage at the output is 12 volts, you will get the output reduced to 5 volts. So this is the basic PWM principle, and you can easily observe this PWM signal by connecting an LED to the Arduino and giving it a PWM signal using analog write instruction. And you can see when you decrease the PWM signal duty cycle, the LED will go on slowly dimming. This is because the voltage reduces as the duty cycle reduces. And now this is a 5 volts 5 ampere current. So this can be taken up using this potentiometer. This buck converter's voltage can be adjusted between 0 to 6 volts. Hence, we set it to 6 volts or 5 volts depending upon the motor using this potentiometer. And an inductor is also an inductor, and a switching IC is used to step down the voltage. Now the current sensors.
Basically, we have also interface current sensor in series with the servers. So the purpose of the current sensor in that, the motors which we have used don't have overvoltage. current sensor protection. If any is added on the robot, it will motor drawing excessive current from the motor. So the motor will end up getting damaged. Hence, the current sensor is used, which continuously senses the current flowing through the individual servo motors. And if the current exceeds a particular threshold value, then the motor or the particular link will be stopped automatically. Mainly, the working of the current sensor we have attached to the in robot because of safety precaution to avoid damages to the motors, and hence the motor and of course robot life will be increases. So basically, if any excessive load is added on a robot, so the current sensor will sense that current and gives analog values to the Arduino from its output pin, and Arduino will read that analog value, and by coding the motor will be stopped because of threshold value. This is the pin diagram of current sensor. You can see on the screen, here is a ground pin, output pin, VCC pin. Basically VCC pin is connected to volt because the operating principle of current sensor, and output pin is connected to the Arduino, which is a analog pin. You can give to the analog pin from A0 to A5. Ground pin is connected to the ground pin. Here is a PWR LED, you can see on the screen. And this current sensor is basically ACS712, 30 ampere current sensor. It is available in 5 ampere, 20 ampere, and 13 ampere. For the many different ampere, you can different sensitivity for that. Here is a, you can see on the screen, current in and current out, which is basically the output from the buck converter, which is grow through this current sensor node and passes to it to the servo motors. So you can see on the screen interfacing of a current sensor with Arduino. Here is a VCC pin is connected to the 5 volt, and ground pin is connected to ground, and output is connected to the A0, which is analog output pin. Arduino has A0 to A5. So you can connect it to the A0 to A5. So I connected it to the A0. So, and in series with current sensor, you can give it the load and battery for that load supply. One wire is going to the load, and another is the battery of main two. So from that, you can measure the current flowing through this load. So okay, go ahead.
So I hope you understood the principle of current sensor. Now moving on to the servo motors. So the main thing in this robotic arm is the motors. So why did we use servo motors? So basically servo motors, the benefit out of servo motors is that they have a feedback. They are nothing but simple DC motors with a feedback mechanism which gives it the name servo motor. Hence, as you can see, there's a DC motor running, and then the gear system for reducing the shaft speed and adjusting the torque is used, and the particular gears drive the output shaft. Hence, the robotic arms, the gears, external gears are connected to this output shaft for driving the particular arms. Now, when the driving shaft moves, it is connected to a potentiometer. Hence, when the driving shaft moves, the potentiometer also moves. The potentiometer for every position gives a particular analog voltage. Hence, this analog voltage is used as a reference output signal, and it is given to an op-amp. Okay, so this basically op-amp is an error detection amplifier, which amplifies the signal given by the potentiometer. And on the other hand, the op-amp is also used as a comparator. Hence, the reference input signal is also given. The reference input signal is given using Arduino via the PWM signal. Hence, the PWM signal goes through the comparator. The comparator compares the analog signal sent by the Arduino and the analog signal received by the potentiometer. Hence, by this, the difference is calculated and the the servo motor understands if the desired position is reached or not. If the feedback is positive, then the DC motor goes in the further direction and achieves the particular angle. If the feedback is negative, hence the DC motor will go the other way around and reduce its angle. Hence, the particular angle is achieved, and using this, we can accurately move the arms to the desired position in the robotic arm. Now, the servo motor, as I told you, runs on a PWM signal. Now, I gave you an example. Different servo motors have different duty cycles. Like the example given here has a 20 milliseconds duty cycle in the entire. Now, if you keep the switch on, the power on for 1 millisecond, and the rest of the time, 19 milliseconds, the power is off. Like the PWM signal is adjusted to this particular level. Hence, the motor will only move 0 degrees and it will stay on its position. Now, if you increase the PWM signal to 1.5 milliseconds duty cycle, so the motor will achieve 90 degrees in particular. So by just giving 1.5 milliseconds PWM signal, the angle can be achieved accurately. Now, if you give 2 milliseconds of signal, and then the motor can achieve 180 degrees angular rotation. Hence, as you can see, it is a very basic principle that when you give a particular PWM signal, the voltage is generated accordingly and the voltage is compared by the servo motors and then it moves to a particular angle. And in this way, we can, in a very simple way, we can control the servo motors and actuate the arms. Now, this is the FETEC motor in the base and the link 1 and the link 2 of the robotic arm multi-gripper. We have used these motors. The reason for using these motors is that they have a very high torque. Like, to be precise, it has 55 ounces per inch at 7.4 volts and 480 ounces per inch at 6 volt. Hence, this torque was the desired torque which we needed for moving our robotic arm particular links. Hence, the base link 1 and link 2 are driven at 7.4 volts using the FETEC FT5335M motor. Now, it basically works on the same principle I explained you before, but the total rotation angle of this motor is 120 degrees, not 180 degrees. So this was sufficient for our application. Hence, we um, chose this motor. Now, also the other motors, MG995 servo motors, are used to drive the wrist and the gripper, that is the end actuator. As you can see, this is a simple setup of running a single servo motor using Arduino. Hence, the power supply is given to a buck converter and which is given to the voltages of the servo motor, and then the ground is made common because if you are interfacing a servo motor with Arduino, the power supply grounds need to be common for the Arduino and the servo motor. And the PWM signal is given via pin number 3 on the Arduino, which is basically a PWM pin, and it is rotated in a continuous loop. Hence, as you can see, the motor goes from this position to its 90 degrees position and returns to 0 degrees. You can set the angles as per you want. This is a basic example we demonstrate to the students. Now, this is the MG995 and FT5335, both the motors which we have used in our multi-gripper. You can see compared to a dollar, compared to a coin, these motors are really small and hence are very suitable for small robotic arm applications or robotic applications in which precise angle can be achieved. Now, I'll explain you a normal code, a small code for running the servo motors, which is basically named as the sweep code. So what happens is, as you saw in that video, the motor was running in a continuous loop from 0 to a particular angle and from that particular angle to 0 degrees back again. In this code, we are moving our motor from 0 degrees to 180 degrees and from 180 degrees to 0 degrees continuously in a loop. Now, the basic format of writing an Arduino code is that first you have to declare the libraries, include the libraries, declare the variables, and then put the setup thing, and then your continuous main load, the main code which you have to run continuously is put in the void loop. Hence, as you can see, we included a library servo.h. This is a very good library for controlling servo motors, and hence you can easily interface servo motors using this servo library. You have to just write the syntax servo.h hash include servo.h. Now, once the library is included, you have to create an object to basically identify your servo and give commands to that particular servo. As you can see, like we have to create an object because multiple servo motors can be interfaced using the single library. Hence, my servo is basically the object name that is given for the particular motor we are using. You can use any name, any variable over here to address a particular motor. It is always advisable to give names of the motors as per the requirements and as per their particular application. So if you are using a base motor and you want to control the base motor, so give the name servo and then write base. So every time you want to address that motor and give a particular angle, you can just use the name base and you can give it particular commands. Now a position variable is initialized, which has a data type of int category with the value in it 0. This position variable, which will be basically used for storing the positions of the servo motor. Now in the setup, we have declared myServo.attach. This is written because we have to let the servo.h library know that on which pin the motor is connected. Hence, we selected this 9 number pin, and we have to make sure that while controlling servo motors, compulsorily use the PWM pins only on Arduino Uno. Hence, now in the void loop, as you can see, we have given a for loop. The for loop is basically initialized from 0, like the value 0, and then it is compared until, and it is run continuously until it reaches the value 180 degree. And every time this for loop executes, the variable POS is incremented by 1 using this syntax. So what we are going to do in this is basically we have the syntax my servo, the servo name, the object name that you gave in the beginning, and dot write. By using this instruction, you can directly write the angle you want to achieve for the particular servo motor. Hence, we use this syntax my servo dot write POS. In this, what happens is every time this loop gets executed, the value increments from 0 to 180 degree one by one, and the servo motor will move in steps. Now, why do we use this thing? Why can't we directly use my servo dot write to a particular angle? It depends upon your application. If jerks and immediate actuating of the motor isn't a problem for your application, then we can write directly my servo.write and the position you want to achieve without the for loop. But in this case, we needed to control the speed of the servo motor. Hence, we also write a delay of a particular 15 milliseconds, and then after every 15 milliseconds the motor will move one step, and hence this speed of the servo motor also can be controlled using this mechanism. Now, once the motor reaches 0 to 180 degree, we have to also bring it from 180 degree to 0. Hence, we write the for loop in this way and then decrement the for loop in each turn, in each iteration one by one, and then decrease the value of the position. And in this way, you can rotate the servo motor from 0 to 180 degree and from 180 degree to 0. Now, you can see the electronic box image of the entire control box of our multi-gripper. So basically, this is the single channel SMPS. These are the buck converters, and these are the buck converters of 6 volts, and these are the buck converters of 7 volts. And the current sensors are also there. And the main Arduino Uno, which is a controller. Now the gripper interface. Basically, the gripper interface is like the gripper, as previously my colleague showed you, that the MG995 servo motor is attached, and this gripper opens and closes using this particular motor. Hence, the only it is connected to Arduino, and the MG995 servo motor actuates with the gripper. And external power supply of 5 volts is power provided for the Arduino and the motor. Now you can see particular images that the robot is picking up a bottle. It can place a bottle on one position, and it can pick up from one position and place it on another using the curvilinear gripper. Now, as you can see, we had designed 2 models for this particular robotic application, multi-gripper. One is this one, and the other 2 are given on the either sides. Now, this is a video of the working, in which you can see the robot picks up the block from one place and places it on the other place. This is the MG995 servo motor mounted on the gripper. This is the base, this is the link 1, and this is link 2, and this is the wrist joint. So basically, looking at it, you can imagine that the same thing is used in industries for pick and place application and for multiple applications. Now, the conclusion is that this particular robot, which we designed, is used for pick and place application from one place to another place. The concept of automobile and robotics are combined in this project. The robot does multiple things. It mainly reduces the manual work done by humans in multiple sectors. It has an open source architecture, hence it can be used for teaching and research purposes. As we told you, we are using Arduino Uno, and our company shares the entire architecture, the entire program, the entire connection circuitry with the students and with the teachers for research purposes, so that they can teach their students to write different codes and do different applications using the same robot. And also they can use it for research purposes and develop something great out of this basic robot. Now, the multi-gripper robot is designed at a very low cost, as well as with a very high efficiency. Thank you. And if anyone has any questions, can either type it in the chat box, or they can unmute the mic and ask it. Thank you.
Thank you, Kaif and Karan, for your presentation. I would now request participants, if they have any questions, to please unmute yourself, and you can ask orally. Right. So I guess we don't have any questions. I would like to thank both the experts, Kaif and Karan, for their wonderful presentation and demonstration of the working of robots. Okay, I think we have one question in the chat. I will just read out. Okay, so the question is, which points are considered for gripping design?
Okay, so this will be basically covered in the next sessions, which will be hosted by the mechanical team. So the mechanical team basically designs the gripper, and if any questions related to the electronics or the GUI coding part, then we can answer it. And also how to select motor for an application is asked by Mr. S.S. Patil, sir. So the answer is like it completely depends on various factors. Basically, the first thing you have to look is that what is your application. If you have to achieve a desired position, a desired angle using the motor, then you have to use servo mechanisms or some kind of feedback mechanism motors. They can be step servo motors or basic servo motors or basic DC motors with encoders, so you can achieve particular angles. If there is the constraint of achieving a particular angle is not there, then we can use simple DC motors. Now there are also simple DC motors as well as BLDC motors. Now according to the efficiency requirements, you can choose the BLDC motors or simple DC motors. As we all know that BLDC motors have a greater efficiency, hence in continuous rotation applications you can use BLDC motors. If you have to achieve a particular angle but your cost is very low, and hence you can also go for stepper motors. Stepper motors basically actuate in steps, and you can achieve particular angles by giving steps to it. Also, the feedback mechanisms can be implemented in stepper motors using an encoder, but it completely depends upon your requirements. The most important thing that you have to consider is the torque of the motor. Depending upon your mechanical design and the weight and the torque which is required, these motors are selected. And there are a lot of variations and miniaturized as well as massive large motors available. You can decide upon which motor you have to use upon the guidelines I gave you, that is the torque, the supply, and the application desired feedback mechanisms. And the next question is that which type of controller is implemented for design? Which type of controller is implemented for design? So basically, I think you are asking about the controller that we chose, and how did we decide on using a microcontroller such as Arduino Uno. So basically, the controller you are using also depends upon your application, as in if you have to use it for teaching purposes. So the controller which should be as easy to use like as possible, because students and teachers both can interact with it easily and also learn it easily and teach things easily on it. The codes are very simple to do in Arduino Uno. It is an open source architecture, hence you can get every single information about Arduino, as well as on the Arduino forums. If you have any doubt, if any application is not working, and if you have to do some desired task, so you can post it on Arduino forums and then you can get feedback. Similarly, Raspberry Pi, Jetson Nano can also be used, but for such simple applications such as controlling just a few motors, you don't need to go for high-end microprocessors. You can just use basic microcontrollers such as Atmega 328P, which is included in Arduino. You can use PIC microcontrollers, or you can use ARM if the application is a bit complex, but it is a lower level application. Is there any servo motor available with dual shaft assembly? Yes, servo motors with dual shaft assembly are available online if you go check. You can get it on the websites, and you can search your particular requirements according to the torque and the voltage which is needed. So you can surely get servo motors with dual shaft.
Hello.
Yeah.
Hi, my name is Arindam Banerjee. I
Hello.
actually wanted to ask a question that are there any errors you face when there is an input and output between the servo motor and the Arduino controller? And
Uh,
does
yeah.
the error percentage change with the power of the servo motor?
Basically, yes. It also, like, we faced a lot of errors while designing this robot. There were a lot of issues, and the main issue that we faced was the EMI and the servo jitter, which is a very common issue while using multiple servo motors together. So basically, what happens is that if you are using a low voltage and a low current servo motor, the possibility of crosstalk between different motors is reduced, because when you give a PWM signal to a particular signal pin of a particular motor, and then at that time you want the rest of the motors to be stable at their position. But what happens is, when you're using servo motors and giving it PWM signals, so there is a possibility of crosstalk. Means when you are actuating a particular motor, the other motors also jitter a bit due to the crosstalk or the EMI interference. So, and as you increase the current and the voltage of this particular the servo motors, the crosstalk, the possibility of these errors also increases proportionally. Hence, that is not that these things cannot be avoided. These things can be completely avoided by actually, like, implementing capacitors between the VCC and ground of the supply. So basically, even what happens is that we are using a simple DC motor also. So back EMF also results in the fluctuation of the power supply. Hence, capacitors can be used to avoid this issue. And also that we came up with the solution of using a ferrite core. The ferrite core, basically what it does is that when the current or the voltage jumps from one wire to another, so it basically charges itself and reduces the EMI interference and completely eliminates it. So at first we were getting this issue that when we were using the base motor, the arm also automatically actuated it. Basically not just actuated, it used to shiver. Hence, after implementing the capacitors and the ferrite cores, we certainly could resolve these issues. And as your question, yes, the voltage and current are proportional to the amount of noise or the jitter that you can get in servo motors.
Hi. One more follow-up question to this. Can you install or keep two Arduino logical controllers to the robot instead of
Yes,
yes?
surely you can add as many controllers you want in the this application, because you can control two different motors with a particular Arduino and two different motors with a particular Arduino, which will also like be helpful for parallel processing, because as Arduino has only a single core, it doesn't support parallel processing. So for these applications in robotics, if we need to perform parallel processing using Arduinos, we use the same technique. We use multiple Arduinos with multiple motors, so parallel processing can also be achieved.
Okay, thank you.
You're welcome.
Right.
So, does anyone have any more questions?
Right. I guess we're done with the questions. I would like to thank again both Kaif and Karan. Thank you for answering all the questions. And again, a wonderful session. From behalf of the Department of Automobile Engineering at RIT and from the coordinators, I would like to thank you both. And now we will take a short break and we would meet back again at 3 p.m. for the next session. So I request all the participants, you may leave this meeting and join back with the new meeting at 3 p.m. for the next session. Thank you.
Thank you, everyone. Thank you, everyone.